Hey everyone, welcome back. Today, we're doing an explainer on something absolutely massive. Well, conceptually massive, but physically microscopic. We're talking about the architecture of coordination compounds. These are the literal, unseen geometric blueprints building everything in the macro world around us. If you've ever found yourself wondering how on earth your blood actually carries oxygen, or why some chemical solutions just glow with these intensely brilliant colors, you are exactly in the right place. So let's just jump straight into it.
I know this topic can seem a little overwhelming at first, but seriously, don't panic. We've got a super clear roadmap today. We're going to cover the anatomy of coordination compounds, hit naming rules and isomerism, dive into theories of chemical bonding, check out color and magnetic properties, and finally wrap up with some real-world applications.
All right, Section 1, Anatomy of Coordination Compounds, the building blocks.
So the concept here is actually beautifully simple. Think of a coordination compound. Some people call it a complex compound, kind of like a VIP section at a club. You've got the central metal atom or ion, right? That's our VIP. It's usually a transition metal playing the role of a Lewis acid because, well, it's got these vacant orbitals just sitting there waiting to accept electron pairs. And surrounding our VIP is the entourage. We call these ligands. Ligands are just molecules, or ions, that willingly donate a pair of electrons to that central metal. For instance, in the hexamine cobalt-3 ion, cobalt is our VIP, and the 6 ammonia molecules, that's the entourage.
Now, this entourage isn't just one size fits all. Ligands come in a bunch of different types based on how many hands, or donor atoms, they actually use to grab onto the metal. Monodentate ligands, like ammonia or chloride, they attach with just one atom. Easy. Bidentate ligands use two. Polydentate ligands, like EDTA, they use multiple atoms, creating these incredibly stable structures through what we call the chelate effect. Oh, and they're even ambidentate ligands. These guys have multiple donor atoms, but can only use one at a time, kind of like being ambidextrous.
Okay, so an absolutely crucial step here is figuring out the charge on our central VIP metal, its oxidation state. Honestly, it's just basic algebra. Take a complex ion like hexacyanoferrate 2. That entire structure has a total charge of -4. Inside it, we've got 6 cyanide ligands, each bringing a -1 charge, right? So that's -6 total. For the whole thing to balance out to a -4, the iron right in the center has to be exactly +2. See? Just simple math, unlocking the chemistry.
Moving right along to Section 2, Naming Rules and Isomerism, the language of complexes.
Naming these things feels intimidating, but it's super approachable if you just stick to a systematic 3-step formula. Step 1, name the ligands first in alphabetical order. Step 2, name the central metal. Step 3, just tack on that oxidation state we just calculated using Roman numerals right at the end. Oh, quick side note, if the whole complex is negatively charged, meaning it's anionic, the metal gets this fancy 8 suffix. You follow those steps, and suddenly a scary chemical formula becomes a perfectly logical name like hexaamine cobalt-3 chloride.
And while we're classifying things, we also categorize these compounds based on the actual makeup of their entourage. It's a really simple binary. Homoleptic means the metal is surrounded by all the exact same type of ligands, a totally uniform entourage. Heteroleptic, that means it's a mixed bag, with a bunch of different types of ligands hanging out in the coordination sphere.
Now, this next part brilliantly illustrates just how dynamic these compounds can be. Think about it like architectural blueprints. You can rearrange them to build totally different houses using the exact same materials. These compounds do the same thing. It's called isomerism. On one hand, we have structural isomerism. This is where the actual physical connectivity changes, like swapping out ligands with counterions, shifting water molecules, or linking those ambidentate ligands differently. On the other hand, we have stereoisomerism. Here, the connections are exactly the same, but the 3D spatial arrangement is totally different. That gives us geometrical cis and transforms, or even optical mirror images. So same exact ingredients, completely different structures. Pretty wild, right?
All right, let's pop the hood. Section 3, Theories of Chemical Bonding, how it all fits together.
So this all started with Alfred Werner. The guy actually won a Nobel Prize for his work on this exact topic. Werner essentially gave us the foundational lens here by figuring out that the metal actually has 2 types of valency. The primary valency, that's just its oxidation state, but the secondary valency, that is the absolute game changer. That's the coordination number, the number of ligand connections. And Werner realized that these secondary valencies are directional. They literally dictate the definite 3D geometry of the entire complex.
Let's see how that builds into Valence Bond Theory, or VBT. VBT basically explains that ligands donate their electron pairs into the metal's empty hybridized orbitals.
Depending on your coordination number, you get very specific hybridizations and shapes. A coordination number of 4, that gives us either a tetrahedral or square planar shape. A coordination number of 6, that locks us right into an octahedral shape. So VBT really gives us the core architectural frame. But here is where we kind of hit a brick wall. VBT is fantastic for drawing shapes, but it has some glaring limitations. It completely fails to explain magnetic properties accurately. And worse, it leaves us staring at a massive, unanswered question. Why do these coordination compounds exhibit such vivid, brilliant colors? VBT has absolutely zero answers for energy levels. So to solve this, we really need a theoretical upgrade.
Which brings us to Section 4, Color and Magnetic Properties, the CFT upgrade.
Okay, so while valence bond theory gave us the basic bonding and the physical shapes, crystal field theory, or CFT, completely changes the paradigm. CFT states that as those negatively charged ligands approach the central metal, they actually create an electric field. This field literally splits the metal's d orbitals, which normally all have the exact same energy, into 2 completely different energy levels. You get a lower energy 2G G set and a higher energy EG set. Honestly, this orbital split, it's the secret key to everything.
Now, the size of that gap, the crystal field splitting energy, isn't always the same. It depends entirely on who's in the entourage. Strong field ligands like cyanide or carbon monoxide, they aggressively push those energy levels super far apart. Weak field ligands like halogens or ammonia, they cause a much smaller split.
And this brilliantly illustrates why these compounds act so differently around magnets. The size of that orbital split dictates exactly where the electrons go. If the gap is small, the electrons just spread out and remain unpaired. That makes the compound paramagnetic, meaning it's drawn to magnetic fields. But if the gap is huge because of a strong field ligand, the electrons are literally forced to pair up, down in the lower energy level. That makes the compound diamagnetic, meaning all the electrons are paired up. Boom! CFT solves the magnetic mystery perfectly.
But what about the color, right? Well, it all comes back to that gap. When white light hits these compounds, the electrons in the lower split level absorb very specific wavelengths of energy and actually jump the gap up to the higher level. We call this a DD transition. And the color we actually see with our eyes, it's just the complementary color of the light that wasn't absorbed. For example, a copper and water complex absorbs red and orange light to make that jump, leaving us to see this stunning, vivid blue. I mean, it is literal quantum mechanics happening right before our eyes.
Finally, let's step out of the micro world for Section 5, Real-World Applications, from Theory to Reality.
Because look, all of this geometry and orbital splitting might sound purely academic, but it literally builds the macro world. This exact chemistry is happening inside you right now. Hemoglobin, that is a coordination compound using iron to carry oxygen through your blood. Chlorophyll uses magnesium at its center to power photosynthesis and basically keep our whole planet green. In medicine, there's a platinum complex called cisplatin that is literally used to fight cancer cells. And industrially, these complexes act as vital catalysts and are used in EDTA titrations. So this isn't just textbook chemistry, it is the fundamental engine of biology and industry.
Really quick, for those of you leveraging this explainer to study, here is your ultimate cheat sheet. Number 1, always double-check your oxidation state calculations. It's your foundation. 2, memorize those common ligand names. 3, actually draw out those structural and spatial isomers until it's just muscle memory. 4, know your VBT coordination numbers and their matching shapes. And 5, really make sure you understand how ligands cause that CFT orbital splitting. Keep this list handy for sure.
As we wrap up this explainer, I really hope you see that mastering coordination compounds proves chemistry isn't just a bunch of theories. It is the core architecture connecting life, medicine, and human industry. From the iron running through your blood to the blue of a copper crystal, it all comes down to geometry and energy. Which really leaves us with a fascinating thought to chew on. What other microscopic designs are secretly running our world right under our noses? Thank you so much for exploring this with me today. Keep asking those questions and keep learning.